Hello and welcome to Module 8, the last module in our course on Introductory Business Statistics. At least in the first course. There is going to be a second course with a few modules of its own, but for now we're coming to the end. So in this module we're going to be looking at these things called interval estimates. So we're going to do the process of estimating intervals. Now, depending on how long it's been since you went through the material covered in Module 7, Module 8 should sound quite familiar. In Module 7, we had gone through how to estimate various point estimates, and so we looked at how do we estimate x bar as a point estimate of mu. So this was a sample mean as our best guess of the population mean. We looked at the sample proportion as a best guess of the population proportion. And we also looked at the sample standard deviation as our point estimate of sigma, the population standard deviation. So in this module, instead of just looking at point estimates, we're going to look at interval estimates. And specifically, we're only going to look at them for proportions and mean. Standard deviations require a different probability distribution that we have not looked at yet. So what do we mean by this? Well, in Module 7 we looked at point estimates, we looked at sampling distributions. So we have some idea of how these sample means are distributed within a population. If this is my population, it has some standard deviation denoted sigma 0 or sigma naught. And we now understand that the sampling distribution, the distribution of sample means, well, that is distributed by the standard error, which is the standard deviation divided by the square root of the sample size. So we have a little bit more information now that we can work with. Similarly, also covered in Module 7, we looked at the standard normal distribution. Now I'm just going to scroll down here and let's give a very brief discussion on what it means to estimate an interval. So if we start with the standard normal distribution, the standard normal distribution we know looks something like this, has a mean of 0, and it has a standard deviation equal to 1. That's not a very good, this should come down here. So using the standard normal distribution and using the tables, we've looked at some of these Z tables in Module 7 as well. I know that I can define certain regions of that standard normal distribution that correspond with a certain level of confidence or a certain probability of an event occurring. So if we are going to talk about a confidence interval, we'll define a confidence interval as 1 minus alpha is equal to my level of confidence. So let's just work first of all and assume a 95% confidence interval. Now at this moment that might not make sense what I mean, but we'll get to this. So if I want to develop a 95% confidence interval, then 1 minus alpha is 0.95, so alpha is 0.05. What does that mean? Well, for now, who cares what this means? This allows us to define the region of our normal distribution that we are interested in. So I can look up in our Z tables two Z values that correspond with, in this case, if I'm going to produce a 95% confidence interval, then I want to define this area here such that if I were to draw a number at random out of this standard normal distribution, 95% of the time I'll draw an observation from between those two Z values. So how can I obtain those two Z values? Well, if this is 95% between those two, then this area out here is equal to alpha divided by 2, which is 0.025. And this area out here is alpha divided by 2, or 0.025. So we denote these something like this, Z 0.025, Z 0.025. So that means that if I draw a number at random out of that standard normal distribution, 95% of the time it will fall between those two limits. So we know we can go to the tables, we can look up these numbers, and for a 95% level of confidence, those two numbers are going to be 1.96 and negative 1.96. Now, if you're wondering where those came from, we can look at our Z distribution here. I know it's a little bit messy, maybe from a previous exercise. And here I've got them already actually drawn out. We have our values of 1.9, here's 1.96, and that corresponds right here with this value of 0.025. So this is where those values are coming from. So you're maybe asking yourself, well, so what? What is this? Who cares? Well, remember, the standard deviation of a standard normal distribution is equal to 1. So I can actually write this as this, that 95% of those observations exist within 1.96 standard deviations from the mean. In the standard normal, that mean is equal to 0. Now let's carry this through to our population distribution. So now if I draw out our population distribution, I'll draw it right below here. So now this is the distribution that has some mean mu, and this has now some standard deviation equal to whatever that is. We don't need to have numbers in here, but it has a standard error equal to sigma over root n. Now, again, within this population distribution, because I know how it's related to the normal distribution, we know this relationship holds. We studied this in Module 7, that the Z is equal to the population, as the sample mean divided by a standard error. So we can convert, we can move between the population distribution and the Z distribution using this formula. So I can drop these lines down. If these come down here, and these come down here, I'm just following these lines down, this point here is 1.96 standard error, so sigma x bar, and this is negative 1.96 sigma x bar. So what this means is that I can identify these two values within my population distribution such that 95% of my sample means will fall within that range or within that interval. So what this implies is that when I take a sample mean, or when I take a sample from my population, 95% of the time that sample mean will fall in here, somewhere within this interval. Of course, that means that there's a 2.5% chance that I'll have a sample mean way out here, or maybe a 2.5% chance that I'll have a sample mean way down here. So there's a possibility that it's outside of those limits, but 95% of the time it will be within that range or within that interval. Okay, so what can we do with that? Well, we defined this between the mean and that upper limit. This distance here, this is what we call our margin of error. And this distance is exactly equal to 1.96 times that standard error. Now, and it's exactly the same on the other side as well. It's exactly the same here. That population mean is exactly in the middle, and so there's one margin of error on each side of that population mean. Now, what we do, and coming finally back to this idea of a confidence interval, if I use this information to construct a confidence interval, I can say I am 95% confident that the true population mean lies within these two limits. How can I say that? Well, let's see. If this is my sample mean here, this x bar, if I calculate the upper and lower limits around this sample mean using exactly this standard error, or sorry, this margin of error, so I say this is plus 1.96 times that standard error. This is minus 1.96 times that standard error. Well, as you can see, if that sample mean lies between those two limits, which 95% of the time it will, then if I construct an interval around that sample mean, with a lower limit here and an upper limit here, I can be 95% confident that the true population mean lies within that interval. And we can see that for any of these. If I take this sample mean and I follow it down, and now this is going to be plus 1.96 standard errors. This is then minus 1.96 times that standard error. Again, here I can see that population mean, I mean 95% sure that it lies somewhere within that interval. That's 95% confidence. Again, that doesn't mean that I'm always correct. There's this chance that, well, maybe I get a sample mean that's somewhere way out here. And so if this is plus 1.96 standard errors, and this is minus 1.96, well, as we can see, it's not always going to fall in that interval, same as if we're out here. But I know that 95% of the time, I will draw a sample that has a mean that falls between these two values, which means that if I construct an interval estimate using that margin of error, 95% of the time, that interval will contain the true population mean. So in this module, we're going to go through a bunch of different calculations using this formula, x bar plus or minus some margin of error, and the general notation will be z alpha divided by 2 times that standard error, where this alpha divided by 2, that is going to be determined by what level of confidence we want to work with. We'll also be looking at confidence intervals for sample proportions, which will be very much the same thing, but our point estimate will be the sample proportion rather than a sample mean. Okay, so I hope that gives you probably a more thorough introduction to this module than I've done for some of the other modules. But it's an important chapter. It's very useful information. As a matter of fact, we can apply this to a wide range of different things, and I think we will in this module. So I hope that was helpful. Thanks for watching. This is the last module. I am going to start working on Introductory Business Statistics 2, and we'll just keep moving forward from here. Okay, so thank you very much for watching, and let's get into some problems. Bye-bye.